Fine, so here I'm going to be looking at this idea of phase change and also molecular behavior when there's a phase change and why the temperature does not change. But before I do that, I actually just want to go back to specific heat capacity and just spend a little bit of time on that. We're going to be using this graph. Now this graph was generated by heating water in a kettle, and I had a temperature gauge in the kettle. Starting off over here, we get the melting point. I actually had ice water mixture, so you had ice water here, and so this was there was a phase change here. There was a phase change as the ice went changed into water, as they went from a solid to a liquid. And here, this section over here is another phase change when it went into a gas. When it went in from a liquid into a gas, that phase change took place here. This section along here is the heating up of the water as it went from just about 0 degrees up to 100 degrees. Now, looking at this part over here, in this section over here, you're going to get the Q is equal to MC change in T. Now, I actually was using a kettle with a power input of about 2,200 watts. That's what it said at the bottom of the kettle. So in other words, the kettle was supplying 2,200 joules per second of energy. Now I have here the slope of this graph is giving the rate of change of temperature. So if I divide by time, if I divide both of these by time, I can put this into power, and then I have my mass C and my rate of change of temperature. And from that, by putting in this 2,200 into here, putting the slope into there, and by knowing my mass, I can work out the specific heat capacity. So in this section, therefore, in this section of this slanted line going up here, we are getting an increase in temperature, and therefore the kinetic energy is increasing, because as we know, the kinetic energy, the average kinetic energy of the particles is indicated by the temperature. But in these cases over here, you'll notice here that your temperature is not really changing during the phase changes here. So during your phase changes, your temperature remains pretty constant. And so here we're having a situation that your EK remains constant. So when you're having a phase change, your EK is equal to constant. Now, what is happening to all the energy that's actually coming in? What's happening here? Because during this time, every second, we are putting, in this case over here, we were putting in 2,000 joules of energy. Well, what was that energy being used for? Well, it was being used to increase the potential energy. The EP is increasing here. Basically, what's happening is that the bonds are being separated. So the molecules, if we view them just as spheres, perhaps they were like this, they are being separated away from each other. You're breaking the bonds and therefore increasing the potential energy of the liquid. So all that energy is going into the increase. Your kinetic energy is staying the same because the temperature is remaining the same. So the kinetic energy stays the same. I hope you've got that clear. If you need any further explanation on that, please come and see me and talk to me about it. So going back to the notes here, I hope you understand these points over here. The process that's taking place in the phase change, basically what's happening when you're going from a solid to a liquid, or reverse, you're getting a breaking of those bonds to the extent that the particles can move more freely not totally separate, but can move more freely. So they can move more freely. You can get some rotational movement. And then when you're going from a liquid to a gas, basically it's a completely breaking those bonds, complete break. And in each case, the potential energy, the PE, the potential energy, is increasing during that time. And hopefully understand why the temperature does not change during a phase change. All that energy is going to increase the potential energy. Okay, so I hope that makes sense. Thank you very much.